All right, we're going to start section 9.8. We have 2 days of notes for this section, and we're going to kind of tie together a lot of the stuff that we learned in 9.7. So now instead of just looking at functions and getting to Taylor polynomials, instead of being given a function, we might be given a series instead. So think of our Taylor polynomials. Instead of writing out the Taylor polynomial of, say, like the fourth order Taylor polynomial p sub 4 of x, instead of writing that out, I might just write the terms as a series. So we already know that these Taylor polynomials approximate functions, and the more terms you use, the higher the order, the closer that approximation is to an actual function. And we've memorized e to the x, sine x, cosine x, and 1 over 1 minus x. We need to have those Taylor polynomials or Maclaurin polynomials memorized because they pop up a lot on the AP test. If you have those memorized, if you think about those terms, like 1 plus x for 1 over 1 minus x, 1 plus x squared plus x cubed, the sum of those terms could be written as what we call a power series. All right, so in a power series, the x would be the variable, and then the n is what's increasing. So a power series would just look something like this. The sum from n equals 0 to infinity of some constant, some coefficient, a sub n, times x minus c, that's the x value, the variable, minus the center, raised to the n power. All right, and remember this coefficient in front might really determine how different the terms look. But we would get like a sub 0, some constant term, times a sub 1 times x minus c to the first power, plus a sub 2 times x minus c to the second power, etc. There'd be some nth term times x minus c to the n power, etc. Now, I'm not putting divided by 1 factorial, 2 factorial, n factorial. That's how we came up with our Taylor polynomials. This is just saying, if I were to generate terms out like this, according to this series, follow whatever this series says, if I were to start showing what those terms would be, those terms can form a power series. The terms match what a Taylor polynomial would be. Okay, so this power series that I wrote up above is centered at C, and we can still think of centers as, excuse me, as points of tangency, because we're still trying to approximate some sort of f of x, like we might be trying to approximate e to the x. We're still trying to show that approximation at a certain point of tangency, and we're coming up with some sort of polynomial that's the best fit. So really the only difference between what we're doing today and what we did before is instead of writing out all of the terms like this, we're going to try to start expressing them in terms of just condensed, like a power series, write it in the form of what I have on the left. A general power series is centered at 0. Think Maclaurin polynomial. So this example that I have above is just shifted either left or right C units, depending on what I have. So again, just think of that C as a point of tangency. So here's a couple of examples of power series. The sum from 0 to infinity of x to the n over n factorial. If I start generating those terms, I get 1 plus x squared over 2 factorial plus x to the third over 3 factorial. That we should know is our e to the x Taylor polynomial. So all we're saying is now we can say, hey, e to the x is really just the sum from 0 to infinity of x to the n over n factorial, rather than getting right to writing out all of these terms. So it's just kind of like, I kind of think of it as like a shorthand way to write that. This next term, this isn't one of the ones we have memorized because it's off center, but it's -1 to the n, so alternating x plus 1 to the n. So here I can see that whatever this power series represents, its center is at -1 because it says x plus 1 instead of x minus c. So it's good to be able to look at a power series and pull out where its center would be. So we already know that e to the x generates these terms and is equal to this power series. And we can show that for any real number x, the series will converge to e to the x. So I don't know if we use that terminology in 9.7, but remember we said the more terms we add on, the more accurately this predicts e to the x. So converges to e to the x just means it becomes e to the x if you could plot an infinite number of points. So that's kind of a good question. Is that true for every power series? So for every function that I have, if I can come up with a power series that approximates that function, is it true that an infinite number of terms would always become the exact function itself? Like, does every power series converge to this function for all values of x, or is it just certain values of x? And that's kind of the question today. Short answer to that, no, they're not all going to converge for all real numbers. So we have something called a radius of convergence and an interval of convergence. So since a power series is a function of x, you'll have some sort of setup that says some function f of x is equal to the sum from 0 to infinity of some setup for a power series, right? Where the domain of f is the set for all x for which the power series converges. So that's kind of our job today, is to figure out, well, what values of x makes this converge? We've done this before, just with less complicated functions. A power series will always converge at the very least at its center, right? Because that center, remember, think of that as a point of tangency. And so the one point where the series matches the function is that center. Okay, so we know that every power series has one value where it converges. What we want to know, is there anything beyond the center? Like if you've got some function and some points of tangency, do the two functions only agree at that one point? That's not a great approximation. Okay, well maybe they agree like at the point of tangency plus a little extra like this, something like this. So our question is, well, how far is that? Okay, so let's look at this. There are three possibilities for convergence. Like I said, we could just converge at a single point. So there's some single point C, the point of tangency, the center, where the series converges, and maybe everywhere else it diverges. Okay, so that would be a radius of 0, because there is no point, there is no distance beyond the center C for a radius of convergence. There is a 0 radius of convergence, so no radius of convergence. That means if we're asked for an interval of convergence, there's not really an interval of convergence either. It's not like x can be between this and this. The interval of convergence is just, I'm just going to write this. The interval is just x equals c. It converges at c. More likely, we do have some sort of an interval of convergence. So there's perhaps some positive radius such that the series converges for the absolute value of x minus c less than r. What is that saying? That's just saying x is equal to any value that's c plus or minus r. Go from the center left or right, r units, radius of convergence. So here's c. Here's a length of r. Here's a length of r. Maybe it cuts off here and here. Okay, so our interval of convergence is like this entire range. That's kind of the picture I drew up here. There's some radius r, so we converge on this interval right here. All right, so what would that look like? Well, r would be some value, so I'm just going to say r is equal to some number, like maybe it's 1 unit or something. Or maybe it's 3, something like that. And so we're just saying our interval of convergence would be c minus r is somewhere, x is somewhere between that and c plus r. That's all we're saying. All right, and then some series do, infinite power series do actually converge to the function itself, meaning they match everywhere. The power series does not then diverge at some point away from the actual function. And so that's easy to think about. That's just all real numbers. Sure, the center's in there. What would the radius be? Well, the radius wouldn't be a number because that indicates like some sort of stopping point. The radius of convergence would be infinity. And I'm not going to write c plus or minus infinity. I'm just going to say the interval of convergence would be something between negative infinity and infinity. All real numbers, in other words. Okay, so those are our three scenarios. Converge at a point, converge on an interval, converge for all real numbers. How do we figure this out? Let's kind of see what this looks like again. I sketched it. Now, if you want to pause the video to type this stuff in, you can. I typed some of this in ahead of time because we've kind of already looked at this, and I didn't want to add time to the video of me just typing things in. So let's look at a geometric series. So remember back to our 9-1 to 9-6 days. A geometric series means some number raised to an n power, and this series converges as long as x is a fraction, right, between 0 and, well, between -1 and 1. If it converges, remember a geometric series converges to the first term, x to the 0 is 1, over 1 minus r. R is x in this case. Okay, so this was one of the Taylor, we memorized this Taylor polynomial. 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the fourth, etc., etc. And that's where that power series comes from. Okay, so anyway, I have graphed 1 over 1 minus x, and I've already typed these functions in. And so I just kind of want to look, let's see. So the blue graph is the 1 over 1 minus x. If we just use the first two terms of that power series, let's look at how the actual function compares to this one. Now we're centered at 0, so I'm going to zoom in a little bit. Well, no, I'm going to just tighten up the window. We'll go to like -5 to 5, and we'll go from like maybe just -5s all around. Let's get that. Okay, so we can see that they share a point right here. Although if I trace on the red line, or no, if I just go to the table and maybe count by like 0.1s, have it start at 0. Let's just kind of see what's happening. They match at 0, but even at just 0.1 away, you can see we're already starting to disagree about what the value is. Okay, so that's not the greatest prediction. What about if I turn that off, add an extra term? So now the black graph is the power series, but it's stopped at a certain number of terms. You can see it matches up a little bit better. Turn that one off. Let's turn on this last one. This is the last one we'll look at. Even more terms, we get even more accuracy. So you can see that radius of convergence is kind of building. Now the question is, if I add more and more terms, is it going to agree everywhere or not? Well, I don't think that my polynomial will be able to match this branch and jump down to this branch over here, right? So is it going to match up exactly? That's something we can investigate with some tests. Now we can do the same thing for sine. I'm not going to take the time to because I think that you might have this graph on your paper, but we've got a sine x function that you can kind of see here. And then we have, depending on how many terms you're going to use, we have a Taylor polynomial. And the more terms we add, the more these two functions actually match up, the further they match up. Now, the Taylor polynomial or the power series for sine x will be exactly the same if we had an infinite number of terms to add. So that radius of convergence is infinite. All right, so what are we looking at? Find the radius and interval of convergence. We had these questions similar to this in our last section in chapter 9. So remember, we were looking at, okay, if x is being raised to an n power, what values of x would make this converge? Now, the difference in this chapter is we have things like n factorial involved or some other expressions you can see. So if there's a factorial involved, to figure out what values this converges for, this is not truly geometric, I would instead need to use that ratio test. And now we have to remember what the ratio test was. Remember, the ratio test is the limit as n approaches infinity. Technically, there's an absolute value here, so if there are any negatives, we force them to be positive. But it's the absolute value of a sub n plus 1 over a sub n. And often this is a complex fraction, so we went straight to flipping it. If you don't have a factorial involved, like number 2 is not too crazy and terrible, then you could kind of think of a geometric series test. Or you could also think of a root test, but I kind of think geometric series. And remember, that's just saying, oh, this thing in parentheses, I'm going to write root test too. Either way, you're kind of saying whatever's in parentheses to the end, take it out of there. And if that limit as n approaches infinity of like, what does that need to be to keep it less than 1? Because if it's less than 1 and, well, absolute value of that, less than 1 or between -1 and 1, if we can show what values makes that true, then this will converge by geometric series test or root test. All right, so for number 1, there's a factorial involved. So I want to look at the ratio test to show what values of x would make this converge. So I'm going to say the limit as n approaches infinity of, I can put the absolute value in. I don't think anything's going to come out positive or negative, but we should have that in there so we have our full set of answers. Okay, so plug n plus 1 into this function. N plus 1 factorial times x to the n plus 1 divided by the original a sub n factorial over x to the n. Now simplify before you take the limit. Simplify what you can. So keep your limit notation. We've done this a few times. N plus 1 factorial over n factorial simplifies to n plus 1. X to the n plus 1 over x to the n. When you subtract your exponents, n plus 1 minus n just leaves me with x. Okay, and as this approaches infinity, I can think of this a couple of ways. Now remember, you're not plugging infinity in for x, so you can kind of think of it as like the absolute value of x times the limit as n approaches infinity of n plus 1. What would that equal? Well, that equals the absolute value of x times infinity, which is infinity overall. So this doesn't even converge, which we could have kind of looked at maybe based off an nth term test, but with the x there, it makes things more complicated. There's not really an nth term test if there's an x involved. Since this came out to infinity, I can say this series diverges by the ratio test. If a power series diverges, then we won't be finding an interval of convergence because it doesn't converge. Okay, where does it converge though? There is one place, right? Even if the power series diverges, there's one place where this converges, which would be at its center. So where is the center? If it just says x right here, then the center is at c equals 0. So therefore, the only place that this divergent power series converges would be at its center. So converges at x equals 0. Radius of convergence is 0, and there is no interval of convergence. If you want to write an interval, I guess you could write something like 0, like that. All right, let's see. What about the next example? This one's not as complicated. This one looks kind of like a nice little geometric series. This would converge as long as, since r is x minus 2, remember, as long as the absolute value of r can stay less than 1, or in other words, as long as r can stay between -1 and 1, this geometric series would converge. So I just have to say that, I guess there are two ways you could write it. You could say the absolute value of x minus 2 needs to stay less than 1, or you could get right to saying that just means -1 between x minus 2 between 1. Solve that, add 2. All right. And then we're saying our interval of convergence is between 1 and 3. Now there's one extra thing we have to check here. We always have to check the endpoints. Now we threw a question like this on the last test that you had, where you had to find an interval of convergence, but some of the answers included the endpoints. And so I was just kind of, that question is on that test to see if you would think about what to do with that. So when we check the endpoints, we're saying, well, what's really happening here? So if I plug in 1, for example, and you would need, for the AP test, you would need to show that you are checking by plugging this in. If you plug in 1, you get 3 times negative 1 to the n. So that's what? 3, negative 3, 3, negative 3, 3, plus 3, minus 3, plus 3, minus 3. So is that going to converge? No, that's not converging to a finite sum. We're just alternating between two terms. Remember, it doesn't pass the nth term test. Okay, so that diverges. And if we plug in 3 for x, 3 minus 2 is 1. We get 3 to the n. That also diverges. Both of those are by the nth term test. Okay, so that just tells me that I don't include the endpoints here. All right, so my interval of convergence is 1 to 3. What would the radius of convergence be? The radius of convergence was before you solved for x, you had x minus 2 is between negative 1 and 1. You're just saying how far are each of these endpoints from the center. So remember, the center is 2. You're 1 unit away from both of those values. So the radius of convergence here is 1. You can kind of see that on this step right here. So the radius would be r equals 1. All right, let's look at example 3. Anytime I see factorials involved, I'm thinking ratio test. So I need to do the ratio test to show that the series converges, and then I will have to think about the algebra to figure out what makes this converge. Remember, ratio test is saying as long as something can come out to a value less than 1, then we're going to get a convergent series. Okay, so let's look at that. The limit as n approaches infinity. Remember, you're doing absolute value here, so do not bother with the negative 1 to the n. Just look at the x to the n part. So x to the, if I plug in n plus 1, that's 2n plus 2 plus 1. So x to the 2n plus 3 over, same thing here, 2n plus 2 plus 1, so 2n plus 3 factorial. Instead of saying divided by another fraction, I'm going to say times. It's the reciprocal of the original a sub n. So 2n plus 1 factorial over x to the 2n plus 1. Don't take the limit yet. There's a lot of simplifying to do. If we start with the x's, 2n plus 3 minus 2n plus 1 minus the quantity 2n plus 1 becomes 3 minus 1, so 2. So x squared. And then how does 2n plus 3 and 2n plus 1 factorial work? Remember, it's just whatever expression you have in here minus 1 each time. So 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So the 2n plus 1 factorials cancel, and you are left with 2n plus 3 times 2n plus 2. Now, in the first example, I had separated out like, okay, so this is, we could pull the x squared out in front and then look at this limit, but either way, remember, you're just plugging infinity in for the n's. So you're going to have some number for x squared divided by this bottom heavy rational expression, right? So you can think of it as having the x squared out here and just having this be 1 over. So either way, you're saying x squared times, this becomes x squared times 0, which is 0. Since 0 is less than 1, I know that this power series converges by the ratio test. All right, that's what we would have done last chapter, or last section. Now, this section, we want to say, okay, it converges, but for how many converges? Sorry, I just realized I misspelled that. For how many values? For all values of x, for just a certain number of values of x, or what? So since the ratio test tells me that this converges because it's going to be 0 times, it doesn't matter what x squared is, right? X squared could be 1,000,000 squared times 0 will still be 0. So since this doesn't matter what x squared is, I can say that it converges with a radius of infinity, and the interval of convergence is negative infinity to infinity. All right. Now, these are not saying they converge to some actual function. Like, we're not approximating a function with these. We're just saying, okay, these converge, but since there's an x involved, do they converge for every value of x or just certain values of x? All right, let's take a look at this one. This, again, kind of looks nicely geometric, right? There are not factorials involved. So I can kind of get right to saying, okay, r will be x plus 1 over 4. And the rule for convergence is that a geometric series converges as long as the absolute value of r is less than 1. In other words, r needs to stay between negative 1 and 1. Okay, so let's equate that to our problem. Negative 1 is less than x plus 1 over 4, which is less than 1. I want to pause here for a minute and point out where this is centered. This is centered at x equals negative 1, because it's not just x over 4, it's x plus 1 over 4. That's important because when you're figuring out your radius of convergence will be looking at the inequality as soon as you got the x plus 1 or the x minus c by itself. So my next step is to multiply both sides by 4. This is showing me that x minus c, your center here, the series will converge 4 units to the left and 4 units to the right. I can say right now my radius of convergence is 4. What about the interval? I solve for x. And I'm not finished because the question is, do I need any equal to signs on either of these? Okay, so for my interval, I don't know yet. I need to check the endpoints. On the AP test, you need to show checking the endpoints and don't leave off your notation or anything. So now you don't have to show yourself plugging in negative 5. You can do this math in your head. If I plug in negative 5, I get negative 4 divided by 4, so negative 1 to the n power. Does this pass the nth term test for series? So go back to the beginning of the chapter. No, because the limit as negative 1 to the n approaches infinity, it's alternating between, it's 1, minus 1, 1, minus 1. So you're not getting a number that's approaching 0. It's either going to be 1 or negative 1. Okay, so that diverges. And it's a similar story for the next part. If you plug in 3, you've got the sum from 0 to infinity. 3 plus 1 over 4 is just 1 to the n. That also diverges by the nth term test. That just tells me that neither of the endpoints can be included in the interval of convergence because we just showed that the series diverges when I plug those values in. So the interval of convergence is negative 5 to 3. All right. Last example. So this kind of looks geometric, but it looks a little more complicated because you have this n plus 1 over here. So anytime I have something in a denominator other than just my expression in parentheses, I think about ratio test. So I want to say I'm going to jump right into ratio test to make sure this converges. So the limit as n approaches infinity, the absolute value, so ignore that part, the absolute value of x minus 1 to the n plus 1. So x minus 1 to the, when I plug n plus 1 into that, I get n plus 2 over n plus 2 times the reciprocal of this, so I don't have a complex fraction. Simplify. So let's see. I can't do any canceling with the m plus 1 over m plus 2. With the x's, I've got x minus 1 to the first power, right? And when I take that limit, I get 1 times the absolute value of x minus 1. Now, is 1 times the absolute value of x minus 1, is that guaranteed to be less than 1? No, it's not. It's not 0, right? So I need to figure out, this will only converges when, let's say, only converges by ratio test when this value, which I'm just going to make absolute value of x minus 1, comes out less than 1, right? Because that's what the ratio test says. If you can take this limit, and in the previous part of the chapter, we took this limit and just got a number. We didn't have an x involved. But if this number comes out less than 1, then it acts like a geometric series, and therefore it converges. So this is just a problem for me to solve now. This means that x minus 1 could be anything between negative 1 and 1. There's your radius of convergence right there. Radius of convergence is 1 because the center is 1. All right, and then solving for the actual interval, if I add 1, I get 2 to 0. I can't answer the interval of convergence yet because I have to check those two values. If we plug 0 in for x, and I'm going to get rid of I scribbled out that alternating piece, but it is important now. So if I put in 0 for x, I get negative 1 to the m plus 1 times 0 minus 1 is negative 1 to the m plus 1 over m plus 1. All right, what's going on with this negative 1 to the m plus 1, negative 1 to the m plus 1? Well, those are the same value, right? They're the same base number. You can add their exponents together if you want. So you could say, well, that's n equals 0 to infinity, negative 1 to the 2n plus 2. It's important that I take it that step further because I need to check. If I see negative 1 to a power, I think alternating series, but is this truly alternating? If you plug in n equals 0, you get negative 1 squared. If you plug in n equals 1, you get negative 1 to the 4th. This is always going to be even, right? So really, this simplifies to just the series from 0 to infinity of 1 over m plus 1. Now, I recognize this as one of those general harmonic series, so I know that this diverges. When you're doing these problems, you don't have to go through and show, I guess this would technically be like a limit comparison test to show that this diverges. You're going to be looking at just the endpoints. You need to show this much work, but I don't have to go further and do an LCT. Okay, so I know that there's no equal to sign on the 0. That doesn't knock out the 2 automatically, so now start over and plug in a 2 into the original, into the original series. Plug in a 2 and see what you get. So negative 1 to the m plus 1. And then when I plug in a 2, I get 1 to the m plus 1 over m plus 1. Now 1 to the m plus 1 is just 1. We don't need that in there. Times 1 is just not necessary. Negative 1 to the m plus 1 does make this alternating. This is an alternating harmonic series, so this converges. I'm going to write in here, alternating harmonic. It's an alternating general harmonic, but we get the idea. Okay, so that means that I can include 2 in my interval of convergence. So the interval is not including 0, but yes, including 2. The radius of convergence is still 1. Even if you're not including one of the endpoints, it's still 1. All right, that's it for today. We have textbook work For homework tonight, I think we're on assignment 23.